It was factoring a cube root. I don't know if factoring is the right term, but we did two questions with the cube root.
Okay. Let's see. Let's see if I can do this correctly. Hmm. Okay, I'm sharing my screen with you guys right now. There's a lot going on. Can you see, what do you guys see right now? Do you see these lecture notes?
Just a blank piece of paper.
Okay. Well, just a blank piece of paper. Let's see. Let me stop sharing real quick. Sorry, I'm trying to do an advanced sharing method. What is happening? Okay. So this is the set of Mary's notes for section 1.6, solving other types of equations. And I'm assuming that you guys started in on solving these rational equations where the form of the equation essentially looks like each of the rational expressions has fractions with more than one term, and you sort of had to examine the denominators to determine if, let's see, she has another, right. Let's see. Okay. Sorry, I sort of got stopped in my tracks. I was just reading a message in the chat. So yes, I'm aware that she has her own set of notes, but I don't have access to the ones where she has written and where it shows where she's left off at. I don't have access to her Canvas course. I was only given access to her Zoom. Um, no, that's fine, Andrew. Thank you for being so helpful, but I think that we can just sort of soldier on. You guys have seen this section already then, right? Solving these kinds of equations that look like fractions.
Yes.
Okay, cool. Um, let's see. Well, usually I like to start my courses by going over any questions that you guys might have about these, but let's go ahead and save that for the end. Um, did you guys cover this power property?
No.
Not yet. Okay, so that's probably the next kind of equation. Um, it sounded like I forget who mentioned this, but it sounded like you guys were solving equations that had cube roots in them. Okay, so this power property is going to be super helpful. Essentially, what the power property is, if I can just read it to you guys, it says if P and Q are algebraic expressions, uh, then every solution of the equation P equals Q is also a solution to the equation P raised to some power is equal to Q raised to that same power for any positive integer n. So as long as, we have an equation where, you might have an algebraic expression, let's say 3x plus 4 is equal to, um, let's say 5x minus 7, something like this. And maybe that's in a radical, like a square root or something like that. So these are two algebraic expressions that are set equal to each other. And so we could call the left-hand side of this equation P. We could call the right side of this equation Q. And that if we wanted to transform this equation by raising these two sides of the equation to some power, as long as those powers were the same and an integer that is a whole number, then we could solve the equation. And the equation, the new equation that we got, so let's say that we raise both of these sides to the power of 2. This new equation that we would get, which doesn't look new because it has some elements of the original equation, but just go with me here. That if we solve this thing now, where this is P raised to some power, and over here is Q raised to some power. Well, this is just a simple linear equation that we can solve by isolating x and then getting the numbers or the constant terms moved over to one side. Once we solve for x, that will be a solution for the original equation. Okay. Now, one thing that you do have to watch out for when applying this power or this power property is that it doesn't say that your P equals Q equation is equivalent to P raised to a power is equal to Q raised to a power. So when you raise both sides of the equation to a power, it only says that the original equation, the solution of the original equation, P equals Q, will be a solution for the new equation, but we have to check our solutions to make sure that that's okay. Let me go ahead and, okay. So that's my recap of the power property. I'm seeing in the chat that you guys were on the last question for the power property. So let's go ahead and sort of jump that way, right? So we're looking at using this power property to solve radical equations. So, these are the steps that were outlined yesterday. We need to isolate the radical expression on one side of the equation, that is the left or the right. Usually I like to keep both sides of the equation positive. It doesn't matter whether we move the radical expression to the left or the right, but I will tell you this, that most students make mistakes whenever that radical is negative. So we want to keep that positive somehow. So then we will raise both sides of the equation to a power that is the same index. That is, we're going to raise it to the same power so that the radical is canceled out. Okay. If the equation still contains a radical, then we're just going to go back to the top and sort of reiterate that process until there's no more radicals in the equation. Okay. Then we will solve whatever equation we have left over, and we need to check each solution that we may get. We may get one or two different solutions. We need to check both of them to make sure that those are valid solutions. Okay. So we will skip to the last question in this particular section, but what you would see is that, like, let's look at the first one just as a recap. When I look at this equation, I can see that we have this radical expression here. So in my head, I want to move this radical over to the right-hand side so we can isolate the radical expression. We would get something like x is equal to the square root of 15 minus 2x. And then you need to be thinking about what is the operation, what is the exponent that is going to cancel out this radical expression, or at least that radical operation. In this case, it's a square root. Okay. So in my head, I might say that the square root and the square operation, or the square exponent, are opposites of each other. They will cancel out. So I can raise both of these sides of the equation to the second power. And that on the right-hand side of this equation will cancel out the square root, which basically frees up the terms that are inside that square root. So we have 15 minus 2x is equal to x squared. Okay. So what we're applying here is applying some exponent to both sides of the equation. And then once you do that, the radical equation turns into either a quadratic equation. So this now is a quadratic equation. It was originally a radical equation. And then we just use whatever methods we need to solve that quadratic. And sometimes it turns into a linear equation. Linear equations we just solve by isolating the x. Quadratic equations have 3 different methods of solving them, but we would just go from there. So usually these equations will, once we apply the power property, they turn into either a linear or a quadratic equation. Okay. So let's just scooch along to see what this last one is. Okay, I think number 5 or 6 is the last one. Did you guys work on number 5 already?
Yes, we did 5 and 6 yesterday.
You also did 6?
Yes.
Okay. Oh, nice. Did anybody have any questions about those? Or do you guys want to see number 6 worked out again?
Yeah, because we didn't really get to finish it. We kind of ran out of time.
Cool. So what I'm going to do is I'm going to go ahead and write this question down on my piece of paper so that I can just work this by hand as opposed to using my computer. So we have the cube root of 5x squared minus 6x plus 2 minus the cube root of x equals 0. And so let me go ahead and stop sharing. Let me go ahead and switch over to my document camera. Okay, can you guys see this okay?
Yes.
There it goes. It should focus now. Okay. So if we're trying to solve this equation, I identified this thing as a radical equation because we have 2 radical expressions. Whenever you hear the word radical, you should also understand that that means the same thing as root. Math is nothing if not a very flowery symbolic language. We have different words that mean the same thing. So in this case, we're dealing with the cube root. And the first step in this process is that we're going to need to isolate one of these terms, right? This is one term inside the cube root. This is another term inside the cube root. We're going to have to move one of these terms over to the other side of the equation so that they're both isolated from each other. Okay. Now, what I would do is say we can just add this term to both sides of the equation so that we can cancel it out from one side, moving it over to the other side. Does that make sense to you guys? What I mean by that is we can add this cube root of x to both sides of the equation. And what that will do is give us a new equation where if you have something, let's say a negative, let's just pretend for a second that this was a solid number like -10. If I had -10 plus 10, I know that that would be 0, so these would cancel out. Well, it doesn't matter if this is a variable trapped inside of a radical. It's still a number. So if I have some negative number and then I add the positive version of that number to it, anything plus its opposite will be 0. So we can say that these will cancel out. On the other side of the equation, we have 0 plus this term. But we should know that 0 plus anything is whatever that thing is. So now we can just say that 0 plus the cube root of x is just the cube root of x. So we can bring the left-hand side of the equation just straight down. Since we've already canceled out this term, this is all we have left over. So I'll just write the cube root of 5x squared minus 6x plus 2. Does anybody have any questions about that?
No.
Okay, cool. All right. Well, now we're looking at this radical equation, and we can see that the index on this particular radical is 3. We're dealing with the cube root. So the corresponding exponent that will cancel out or eliminate this radical is the third power. So what I need to do is use my power property, which says that I can raise both sides of the equation to some power to cancel out the radical. I'm going to raise both sides of the equation to the power 3 so that that will cancel out my cube root and that exponent. So it'll cancel out over here on the right-hand side, the cube root and the exponent. So that now all we have left over is the contents that were inside the radical expression. So we have 5x squared minus 6x plus 2 is equal to x. Okay. Well, now that we've done that, this is transformed into a quadratic equation. And in order to solve a quadratic equation, typically we get that quadratic equation into standard form, which is ax squared plus bx plus c equals 0. So that's telling me that I need to move this x over to the left-hand side so that I can get this quadratic equation in standard form. So I will just simply subtract the x over to the other side. These x's cancel out, which gives me 0. And then I should have 5x squared minus 7x plus 2 is equal to 0. So there we go. We have that in standard form. Okay. Now, does anybody know what would be the next step in solving this equation? Now that we have it in quadratic form or standard form.
Would it be the factor?
Yeah, absolutely. So whenever I see a trinomial that's quadratic, I always want to think about using the AC method or whatever factoring method I can to factor this trinomial. So I assume that Ms. Cottier taught you guys to factor using the AC method.
Using the what method?
AC.
We did FOIL and then forgot what the other one was.
Factoring out the GCF.
Yeah.
Okay. The FOIL method is not one that I'm super familiar with. It's not one that I teach my students. Do you guys usually multiply this 5 by the 2?
Yeah, we did that before when we did grouping.
Okay, yeah. Okay, so I'm going to factor this. If you guys have any questions, just like stop me, just holler out and ask me what I'm doing if it gets too confusing. But I teach this calling it the AC method. And the reason why we teach it and call it the AC method is because you label the quadratic, right? Where this is A, B, and C. Those are our coefficients. And we're going to start off this method by multiplying the A and the C. Okay. So 5 times 2 would be 10. And then we need to look at all of the factors of 10 that will either add or subtract to give us 7, that middle term, that negative 7 here. Now, I don't typically worry about the sign at first, but let's just factorize 10. So 10 would be 1 times 10, 2 times 5, 3 times 3 and a third. Just kidding. That would be it. These are the factors of 10. And we have a factor pair here that looks like it'll give us 7, right? 2 and 5 somehow will give us 7. But if I add them as positive terms, I would get 2 plus 5, which is positive 7, and I need a negative 7. So in this case, I will go ahead and call this -2 and -5 because both -2 and -5 multiply to give us +10. And when you add these, they give you the -7. So those are the two conditions that we need in order to correctly select our factor pair here. Does that make sense to you guys?
Yes.
Okay. Now, once we have correctly selected our factor pair, we'll go back to the original problem. I usually take this middle term, the -7x, and I split it up into two terms, one being, notice that I have a 5 on the left of this middle term and a 2 on the right of the middle term. So what I'm going to do is I'm going to put the -5x here and the -2x here. It doesn't matter what order you put this in, but essentially I'm breaking up this middle term. So these two terms, if you were to combine these like terms, you would get the original term. And I'll just bring my 5x squared down, and I'll bring my +2 down. So what the AC method is essentially doing is it's a way of taking a 3-term polynomial, breaking it up in terms of this middle term into a 4-term polynomial, and then we could just factor by grouping, right? I usually draw a little dashed line here just as a visual cue, because, right, we want to look at the first two terms and ask, what is their greatest common factor? What do they have in common? Well, these two terms have a 5x in common, so I can just factor out a 5x. And in parentheses, I should be able to put two terms here that when I multiply or distribute this 5x, it gives me the original two terms back. So I know that 5x times an additional x would give me 5x squared. I know that 5x times a -1 would give me my -5x here. Additionally, on the right-hand side of this little dash line, I know that these two terms have a 2 in common. That is for sure. But this first term is negative, so I'm going to factor out the -2. And what I need to multiply in here by the -2, so I get the original two terms, are -2 times x. That returns the -2x. And -2 times -1, which will be negative times a negative, which gives me the +2. Okay. So now that I've done that, you might notice that the stuff in parentheses is the exact same. We have x minus 1 in parentheses over here, x minus 1 in parentheses over here. So that means that this is now a common factor that we can factor out of our expression. So we will have x minus 1, and the remaining bits, this 5x and this -2, that will be your other factor, 5x minus 2. So these two polynomials multiply or distribute to give us our original trinomial. Okay, and since we were solving this equation and it said equal to 0, now we can use what's called the zero factor property to continue solving the quadratic equation. But does anybody have any questions up to this point?
I don't.
No.
Okay. So we'll go ahead and take our x minus 1 and our 5x minus 2. Just go ahead and rewrite that. Those are set equal to 0. And we need to use the zero factor property, which essentially is saying that if you have something and you're multiplying it by something else and you're getting 0, that is, if we have a times b and if that's equal to 0, what that means, so if a times b equals 0, then either a is equal to 0 or b is equal to 0. Okay, so what I'm saying here is that either x minus 1 is equal to 0 or 5x minus 2 is equal to 0. So that quadratic equation, essentially, once we factorized it and used the zero factor property, that decomposes the problem now into two linear equations. So now we're just solving for x. We're just trying to get x by itself. So on the left-hand equation, it's really simple to just add 1 over to the other side, and we can isolate our x. So x is equal to 1. And then finally, for this other equation, we could add 2 over to the other side. So that'll cancel out the 2. We have 5x is equal to 2. Then we can go ahead and divide both sides by 5 to cancel out the 5s. And we should have x is equal to 2/5. Okay. So sort of a lot of work, right? These are our two potential solutions. Okay. So at the start of this equation, we had a radical equation, but when we raised it to the power 3, and we applied that power property, we somehow changed the equation. Now, the equation that we solved here, this quadratic that has two solutions, those solutions may or may not be valid for the original equation. So we have to go back and check to make sure that those solutions work in the original equation. So the original equation was the cube root of 5x squared minus 6x plus 2 minus the cube root of x, and that's supposed to equal 0. Now, did Miss Collier go over a method for quickly checking these solutions? Or are you guys doing it by hand where you plug 1 into x for all of the expressions?
She shows us how to write it out with the x plugged in, and then we just solve it on our calculator.
Oh, okay, cool. Yeah, that's going to be a lot simpler. Seems like my calculator's battery's dead. Luckily, I have 2 calculators. It would be really unfortunate if both of these batteries were dead. No matter. So if we were going to plug in this first solution, we would have to evaluate the expression 5 times 1 squared minus 6 times 1 plus 2 inside the cube root minus the cube root of 1 and see, does that equal 0? Well, I think that this expression might be easy to do by hand because we're not dealing with a fraction here. I'll do the fraction one in the calculator. So this would be, let's go ahead, and that would be 1, 5, 5 minus 6 would be negative 1. Okay, so that would be yeah, I already messed up in my head. 5 minus 6 is negative 1 plus 2. Yeah, that would be 1, the cube root of 1 minus the cube root of 1 is equal to 0. And the cube root of 1 is just 1. Cube root of 1 is just 1. So we can ask ourselves, is 1 minus 1 equal to 0? And we can say, yep, that's true. So this equation, or this solution rather, is correct. Okay. So let's see if I can go ahead and plug the other one into this calculator. Let me zoom in. don't have a whole lot of practice with this fancy calculator, so just bear with me. We have to type in 5x, so I'm going to put parentheses, and then we need to put 2/5 in there, so 2 divided by 5 is the same thing as 2/5, raised to the second power, minus 6, and then x is 2/5, plus 2. And then I need to subtract from that the cube root. Let's see. Subtract from that the cube root of 2/5. Oop. And enter. Okay, well, it looks like I'm getting 0 as well. So it looks like both of those solutions check out. Does anybody have any questions?
No.
Okay. What a fancy calculator. Okay. Okay. So now, yeah, we should be solving now equations with rational exponents. This is another type of equation. In fact, in this section, you're solving 4 different kinds of equations. So really, this is some new stuff. I don't think you guys have seen it yet. Equations with rational exponents are essentially anything that has a fraction for an exponent. Okay. Contains a variable or a variable expression raised to a power that is a rational number or a fraction. Okay. To solve this type of an equation, we need to raise each side of the equation to the reciprocal of the exponent that we see. Okay, so I think that maybe one method of learning this particular type of problem is to just jump in and see what we have here. So let's go ahead and look at this first equation. Okay. And I know that the notes are sort of typed out a little bit weird. Some students confuse this for x times 3/5, but it really should be x with the little exponent of 3/5 up here. And that's equal to 27. Okay. Now, there's an exponent property that will be super helpful here for solving these kinds of equations. And actually, there's a couple of exponent properties. The first one, I would say, is the power to a power property. And that is essentially stating that if you have something raised to a power, let's say x to the n power, and then you raise that to another power, then we need to multiply those powers. Okay. But the other exponent property that's going to be helpful that was mentioned here in the notes is the reciprocal power property. Which is essentially that if we have x, and let's say that we were raising that to, I'm going to say a over b. Let's go ahead and make it a fraction. That if I were to take that expression, x raised to the power a over b, and if I were to raise that to the reciprocal power, which would be b over a, well, according to the power to a power property, we should be able to take this fraction and multiply it by this other fraction. So we would get x raised to the a over b, but we would need to multiply that by b over a. Well, can anybody tell me what a over b times its reciprocal would be?
1.
Yeah, it would just be 1, since anything times its reciprocal is 1. And since we have x to the 1 power, we could just call that x. Right? And usually when we solve these equations, we're going to want to isolate the x, and that usually is our solution. Okay? So keeping this set of notes in mind, right? And we turn our attention back to the original problem. X raised to the 3/5 power is equal to 27. What reciprocal power could we apply to this side of the equation so that we can eliminate this exponent?
Would it be 5/3?
Yeah, exactly. So what I could say is, if our original problem was x to the 3/5, and that's equal to 27, notice I'm giving myself a little bit of space this time. What I'll do is, I'll go ahead and apply to the left-hand side of the equation the power 5/3. Now, anything I do to one side of the equation, I must always do the exact same thing to the other side. Okay? But the takeaway here is that once I multiply out these exponents, 3/5 times 5/3, those cancel out to be 1. So then on the left-hand side, I could just say that this is simply x, since 3/5 and 5/3 will cancel out. And I will have 27. Nothing on the right-hand side of this equation canceled out, so I still need this 5/3 power. So since we've isolated the x, you might be tempted to say, okay, let's call it a day. 27 to the 5/3 power is the answer. But we can actually go ahead and evaluate that in the calculator, right? So we don't want to leave this as an exponent expression. We want to go ahead and evaluate that. So what we might do here is simply in our calculator. Don't know if you can see this, 27. We'll just raise that to the, what power are we using? 5/3. And we get 243. So x is equal to 243. Does anybody have any questions about that? Seems a little bit deceptively simple.
So you just plug the 27 raised to the 5/3 into the calculator?
Yeah.
Okay. Thank you.
Yeah.
Pretty easy, it seems.
So that's one way of doing it. The other thing is that when you have a rational exponent is the same thing as thinking about this. Let's say that I have x to the n over m power. What I teach my students is that the numerator of this exponent, you can think about as a power. The denominator of this exponent, you can think about as the root. of the expression. So we could rewrite this if we wanted to as x to the n power, but the mth root of that expression. So the mth root of x to the n power. Or you could write it as the mth root of x and all of that raised to the nth power. Both of these would be fine. And the only reason I bring this up is because at the end of our equation, we had x is equal to 27 to the 5/3, right? Well, if we wanted to solve this by hand, well, in the event that whatever, something happens where you don't have access to a calculator, what you could do is use this set of rules to say, okay, we have 27 raised to the 5/3 power. If I label the top as my power, so our power is 5, and our root is 3, then that means that I'm taking the third root of 27, or the cube root of 27, and then whatever that is, I'm going to raise to the power 5. So you could think about it like the cube root of 27 raised to the power 5, which is essentially using this format here. And then if you're, quick with your cube roots, or, you have some way of solving that cube root that doesn't involve your calculator, because we've already said that for whatever reason, we don't have access to it. The cube root of 27 is simply 3. So this internal part is just 3, since 3 times 3 times 3 is 27. And now all we have to do is apply that 5th power, which would be annoying to do by hand, but we could do it for sure. 3 times 3 times 3 times 3 times 3. Well, this would be 9. This would be 9. Then the 9 times 9 would be 81. And so then we would just have to multiply the 81 times 3, and I guarantee you that you would get the 243 or whatever it was that we got before. Does that make sense?
Yes.
Okay. Okay, so let's go ahead and scroll on through. Let's look at the next problem. So, this set of notes says that an equation with rational exponents contains a variable or a variable expression. So this number 7 we worked on just had a single variable. Part B of this question has a variable expression. We have x minus 4 raised to a fractional exponent. Okay, but it doesn't matter. We're going to use the same idea here to solve this equation. So let me go ahead and rewrite it. So we have x minus 4 raised to the 2/3 equals 16. And according to our lecture notes, we have to use the reciprocal exponent, or the reciprocal power, to eliminate whatever exponent we see there. So what will be the reciprocal power that we need to use or apply to both sides of this equation?
Three halves.
Yeah, exactly, 3/2. So I'm going to go ahead and apply the power 3/2 to both sides. And here you're going to want to be careful, because technically we're using, like I said before, the top of this fraction that we're applying is a power, but the bottom, or the denominator, is a root. So essentially what we're doing is using a square root right now. And I just want to be able to identify that we're using a square root, which is an even root. Okay, so we just applied an even root to both sides of the equation. That means that, all things are going to work pretty much the same. This exponent here, since it's the reciprocal of this exponent, will cancel out, leaving us with x minus 4. Are you guys okay with that?
Yes.
Okay. But because we used an even root here, we need to bring in a plus minus symbol to the equation. So we need to have plus or minus whatever we get when we take 16 to the 3/2 power. You know, we could throw this in the calculator, but it's going to be really important that we have that plus or minus right here. Now, this only works, you only have to do this for even roots. So whenever you apply an even or a denominator, sorry, when you apply an exponent that has an even denominator, that's when you need to bring in the plus or minus. Okay. Well, if I wanted to, you know, do some scratch work to evaluate 16 to the 3/2 power, I know that this is the same thing as the square root of 16, and I could raise that to the 3rd power. Square root of 16 is just 4. 4 to the 3rd power is going to be 4 times 4 times 4, which would be 4 times 4 is 16. 16 times 4 should be 64, I think. Let me just double check that. 4 raised to the 3rd power, 64.
Yes.
Okay. So that means that we have now our equation x minus 4 is equal to plus or minus 64. So you could think about this as being two equations that we have to solve. So you could think about it as x minus 4 is equal to positive 64 and x minus 4 is equal to negative 64. So when we solve these two equations, we will have two solutions. We can add 4 on this one to get x is equal to 68. And we could add 4 to this one to get x is equal to negative 60. So those would be our two solutions, but I would say you should probably get into the habit of checking your solution every time you get a solution, just to make sure that it works. Again, I'm not going to go through the whole rigmarole of plugging these solutions in because I think that it's going to eat up a lot of class time. But essentially what we would do is just plug 68 back into the original expression. So we're going to plug it right back into x and see if we get, you know, when we have 68 minus 4 raised to 2/3, does that give us 16? You know, and we could throw that into the calculator really quickly. Let's see. Let's see if we can do it really quickly. 64 minus 4 in parentheses raised to the 2/3 power. And let's see if we get.
Was it 64 or 68?
Oh, I'm sorry. You're right. 68 minus 4 raised to the 2/3 power. And yeah, that one comes out to 16. We could do the same thing with negative 60 minus 4 raised to the 2/3 power. And that one also comes out to 16. So both of our solutions are valid in this equation. Does anybody have any questions, comments, or concerns about that?
I don't.
Okay. Cool. I'm going to go ahead and clear this. and let's just continue moving along. Okay, yeah. So those are basically the two flavors of these equations with rational exponents. Okay. This last set of questions is the fourth and final type of equation that we're going to cover today. Well, you know, the fourth and final type of equation that you're going to cover in this section. You guys have covered the other equations before today. But in any case, we're looking at equations that are said to be in quadratic form. If they can be written as AU squared plus BU plus C equals 0, where A is not equal to 0 and U is some algebraic expression. So what does that mean? Essentially what we're saying is that if you look at this equation, let's look at this one that we need to solve. It sort of looks like a quadratic equation, because a quadratic equation usually is in the form ax squared plus bx plus c equals 0. However, there's a difference here. If we look at these exponents, we have an exponent of 4 and we have an exponent of 2. So it's almost like we've doubled the numbers for these exponents. Okay. Now, because it looks really similar to a quadratic equation, we're going to be able to solve it by doing a quick substitution. So what I mean by that is, let's pretend for a second that we're looking at this equation and we're going to take a look at x to the 4th power and x to the 2nd power, right? Usually our quadratic equations are of the form ax squared plus bx plus c. But in this case, we have x to the 4th and x squared. So is there a way that we could just go ahead and let's say substitute in, instead of calling this one x squared here, let's just call that u. And instead of calling this one x to the 4th, we'll call that u squared. So what I mean by that is that if we say let x squared equal u, or in other words, let u equal x squared. Well, if we were to square both sides of this equation, then u squared naturally would be x squared squared, but if we raise something to a 2nd power, then x squared squared would be x to the 4th. So what I'm saying is that we can take this original equation and call it 12. Since we have x to the 4th here, we can just call that u squared. So we have 12u squared is the same thing as 12x to the 4th minus 11, and we're calling x squared u. So I'm just going to substitute that u in there. Plus 2 equals 0. Does anybody have any questions about this substitution that I just did? Does it seem strange?
Yes. So what happened to the x raised to the 4th?
It's still there. X raised to the 4th is equal to u squared.
Okay.
Right? Essentially what we're doing is we're calling x to the 4th a different name, right? We'll think about it this way. We're calling x squared u, so that we can call x to the 4th u squared.
Okay, I understand that now.
So now that we have this in quadratic form, we can solve this as though it's a quadratic equation. Now we need to keep in mind that the original variable that we're working with is actually x. It is not u. We have made the substitution by calling x a different name. We can do that all day, but at the end of this thing, when we solve this quadratic that we have in terms of u, we'll have a solution in terms of u, but we're going to want to back transfer that so that our solutions are in terms of x. Okay. So we're sort of transporting ourselves into the u substitution world. And when we solve this equation, when it's finally solved, we need to be back in terms of x. Okay, so let me run through how this would work. First, we need to make that substitution. Okay, so 12x to the fourth becomes 12u squared. Minus 11x squared becomes minus 11u. The constant stays the same, so plus 2 stays plus 2. But now we're going to solve this quadratic equation. Okay. So we'll solve this quadratic equation the same way we solve any quadratic equation. We'll factorize our trinomial. So if I was going to label this as A, B, and C, then I would multiply A times C, which in this case would be 12 times 2. And that would give me 24. And then I need to look at all the factors of 24 to see, are there any factor pairs that when I add or subtract them, they somehow combine to give me negative 11. So we have 1 in 24, 2 times 12, 3 times 8, and you could stop there if you wanted to, 4 times 6. I like to make sure that I have all of the factors before I stop, but it's looking like 3 and 8 are going to be pretty promising if I make them a negative 3 and a negative 8. Right. Again, negative 3 and negative 8 will multiply to give me my positive 24. And if I were to add them together, they would give me my negative 11. Okay. So I can go ahead and take this middle term and I'll break it up into negative 3u minus 8u. And I'll bring my other terms down. So I have plus 2 on this side. I have 12u squared over here. Of course, all of this is equal to 0, but I tend to just forget about that until I'm done factoring. Okay. So does anybody have any questions up to this point? Okay. Well, if I look at the first two terms, 12u squared minus 3u, both of these terms have something in common, and that is 3u. So if I factor out a 3u there, that means what I have to have left over needs to multiply to give me those original terms back. So I should have a 4u, since 3u times 4u will give me my 12u squared. And then I should have a minus 1 here, since 3u times negative 1 will give me my negative 3u. For the last two terms, it looks like they just have a 2 in common, but since that first term is negative, I'm going to factor out the negative GCF. So negative 2 comes out, which should leave me with 4u minus 1 also. Again, if I distribute that out, negative 2 times 4u gives me my negative 8u. And negative 2 times negative 1 gives me the positive 2. So that should be correct. You'll notice that the stuff in parentheses is the exact same. Those have to match. If they don't match, then I've done something wrong. But since they do match, that means that they're the greatest common factor. And I can pull the 4u minus 1 out to the front, and whatever's left over, the 3u minus 2, that will be the remaining factor. So those factors we can then set equal to 0. Okay, so let me write this down really quickly because I'm gonna have to erase the screen. We have 4u minus 1 as one of our factors and 3u minus 2, and that's equal to 0. Has everybody written this down, or are we cool to proceed is what I'm asking.
Yes.
Okay.
Yes.
Cool. Okay. So we've taken this, we've transformed this into 12u squared minus 11x, sorry, not x, u. And you don't have to use the variable u if you don't want to. You can use any variable name that you want. But for whatever reason, in all the math books, they always use u as the substituting variable. And then we've taken that, and now we've factorized it into 4u minus 1 times 3u minus 2, and that's equal to 0. Well, now we can solve this using the zero factor property the way we do any quadratic equation. So 4u minus 1, set that equal to 0, or 3u minus 2, set that equal to 0. And if you just take a brief moment to, add the 1 over to the other side and then divide by the 4, then we should get u is equal to 1 over 4, and that should be positive. And then over here on the other side, we would add the 2 over to the other side, so that'd be positive 2, divide the 3 over to the other side, so you should get u is equal to 2 over 3. Are you guys okay with that?
Yes.
Okay. Now this, if you're feeling a little bit, when you're working on these problems, it's easy to, with multi-step problems, to feel a bit fatigued. And a lot of students will sort of jump the gun and say, okay, my solutions are 1/4 and 2/3. But you have to ask yourself, what was the variable that we started with? This question asked us to solve this equation, which had variables in terms of x. And we went ahead and said, let u equal to x squared, so that we could say that u squared is equal to x to the 4th, right? But the important thing is that we need to switch back into the world of x. And to do that, we need to use this definition that we gave, that we created, that u is equal to x squared. So wherever we have a solution in terms of u, like u equals 1/4, we really need to switch that back to x squared is equal to 1/4. The same thing over here. We need to switch this to x squared is equal to 2/3. Well, since we have an exponent now in our equation, we want to get our solution in terms of x. That is x by itself, not x squared. So what we need to do is somehow eliminate our square, right? Or the exponent of 2. Does anybody know how to, looking at this first equation, x squared is equal to 1/4, how would we eliminate this x to the second power? How would we eliminate the second power?
Using a square root?
Yeah, exactly. We're going to use the square root property, which says we can take the square root of both sides. Okay. When we do that, though, whenever we use a square root like this, we'll get x is equal to, and you have plus or minus. You got to remember that plus or minus. And I'll leave this as plus or minus the square root of 1/4. This could be rewritten in a different way. Actually, yeah, let's go ahead and simplify that a little bit. Let me back up to give myself some more space. So if we did that and took the square root of both sides, we would have x is equal to plus or minus the square root of 1/4. And the only reason why I say that we can simplify this is because we can take the square root of 1 and we can take the square root of 4. So we would get plus or minus, take the square root of 1 over the square root of 4, and we should get plus or minus 1/2. So that's actually two solutions there. We have positive 1/2 and negative 1/2. Okay. So that is two of our solutions. And then we can do the same trick to the other equation that we have. So we have x squared is equal to 2/3. So we can take the square root of both sides of that equation so that we get x is equal to plus or minus the square root of 2/3. And we could go through a process called rationalizing the denominator to sort of quote unquote simplify this expression here, the square root of 2/3. But I'm just going to go ahead and leave it alone because I don't see a point in simplifying that further. You can't take the square root of 2, nor can you take the square root of 3. So we could just stop there if we wanted to. Okay.
On the answer for the 2/3, we need to use plus or minus.
Yes.
Okay, because I thought we only had to use it if the bottom one was even.
If the exponent that you're using has a denominator that is an even number. So what I'm saying is that when you take an even root, so that's how you want to think about that. If you have an even root and you use an even root, then you need the plus or minus symbol. And we did use an even root. We used the square root, right? So if you think about the square root of x, this is technically the same thing as x to the 1/2 power. And this, remember, the denominator of the exponent is the root.
That would be in comparison to like using like a cubed root, correct?
Right. So odd roots, you don't have to worry about plus or minus. It's just if this is a 2 or a 4 or a 6 and so on, right? Odd roots don't have more than one solution. So I could say plus or minus, and then I'll go ahead and throw a circle around this and X that out. No plus or minus. So just make sure that you have that clear in your head. On those previous problems, it didn't have to, it has to do with the exponent if it's a fraction. But these are just regular fractions. They're non-exponent terms. So it doesn't have, the plus or minus will go with both of these. It doesn't have to do with the denominators here. It's specifically when the exponent is a fraction. That's when you look to see, you know, did you apply an even root? And if you did apply an even root, then you do need that plus or minus symbol. Does that make it a little bit more clear? So for this particular problem, our solution set contains positive 1/2, negative 1/2, positive the square root of 2/3, and negative the square root of 2/3. So there's 4 solutions to this kind of a problem. And one thing I do want to point out is that if we look at the original problem, the highest exponent, which is sometimes called the degree of the polynomial, is a 4. And that tells you right off the bat that there's going to be 4 solutions. So the highest exponent sort of tells you how many solutions there are going to be in the equation when you're dealing with a polynomial. That's why when you guys learned about linear equations, x to the 1 power, you only had 1 solution. When you learned about quadratic equations, where it had x to the 2nd power, you had 2 solutions. And now for these that have x to the 4th power, it's a polynomial. I'm not sure if we're calling them polynomials yet, but so I might have gotten ahead of myself. But that highest exponent tells you how many solutions are going to be. Does anybody have any other questions, comments, or concerns about this problem? Okay. Let me go ahead and clear the screen. And let's keep on chugging. All right. Okay, can anybody tell me what is the first step that I'm going to take to solve this equation?
Substitute.
Set x equal to u,
Yeah, essentially, right?
or u
We're-
equal to x.
Yeah, we're going to say let u equal x squared. Okay, so that's how we want to start off each of these, because then we could take this term and call it negative 29u, since we're replacing the x squared part. And if we do that, then we could take this first term and call it 18u squared. Then we can throw the 3 in there, set that equal to 0. Okay, does anybody have any questions about that, or is that still a little bit confusing? Okay. So since we made that u substitution, we can go ahead and solve this the way we'd solve any quadratic equation. We can start by trying to factorize our expression here. So we might have to take 18 times 3. 18 times 3 is going to be a large number, I think. I feel like I should know this off the top of my head, but that's okay.
54.
There we go. So we should be looking at 54 and all of the factors of 54 to see what will give us 29. So 1 in 54, 2 and 27. You could probably stop there because it looks like 2 and 27 is going to work if we make those negative. Right? So I can go over here, take this and break it up into negative 2u minus 27u. And then I'll just go ahead and write plus 3 here, 18u squared there. And then I can factor by grouping now that I have 4 terms. Okay, so again, I sort of like to draw this little dashed line. I think it's a good visual aid. The first two terms have a 2u in common, so I'm going to factor that out. So we should get 9u minus 1 here. Is everybody okay with that? I will take your silence as a resounding yes. So we'll move over to the second two terms. The second two terms have a 3 in common. Again, this first term is negative, so I'm going to factor out a -3, which will leave me with a 9u minus 1. Again, if I were to distribute or FOIL that out, -3 times 9u gives me my -27u. My -3 times -1 gives me the +3 back, so that should be good. Another indicator that we're on the right track is that the stuff in parentheses matches. We have 9u minus 1 on one side and 9u minus 1 on the other side. Those have to be exactly the same, otherwise I've made a mistake. But since I haven't, and I assure you that I do make mistakes from time to time, you can ask any of my students, 9u minus 1 is the common factor that we can pull out to the front. And then 2u minus 3 is the other factor. Now we can set these factors equal to 0. Okay, so 9u minus 1 is equal to 0, or 2u minus 3 is equal to 0. So that means that if I add 1 here and here, then I will get 9u is equal to +1, which tells me if I divide the 9 over to the other side, I'll get u is equal to 1/9. And then similarly, on the other equation, I can add 3 to both sides. This will give me 2u is equal to +3. And then I can divide the 2 over to the other side, so I get 3 over 2. Okay, I know that went a little bit faster, but does anybody have any questions, comments, or concerns, or do you guys need a second to catch up?
Yeah.
Okay. Are we done here?
No, we need to change it back to X.
Yes, exactly. Okay, so just be mindful of that. Since our equation was in terms of X, our solutions need to be in terms of X. So you could think about switching this equation. Instead of being u is equal to 1/9, we could call u by its real name, which is x squared. And that's equal to 1/9. And we can solve this thing, right? X squared is equal to 1/9. All we need to do is take the square root of both sides of this equation so that we can cancel out that square. So that and that cancel, leaving us with just x. And then x is equal to plus or minus. You can take the square root of 1 and you can take the square root of 9. So we could just call that plus or minus 1/3. So there's 2 solutions there. But we should have a total of 4 solutions. So I can take this other solution in terms of u, which was 3 over 2. And then we can call u by its actual name. So we have x squared is equal to 3 over 2. And we can solve this equation just like we solved that last one. So we'll take the square root of both sides. So we have x is equal to plus or minus. I can't take the square root of 3. I can't take the square root of 2. So I'll just leave this one alone and call it the square root of 3 over 2. So that's 2 solutions there for a total of 4 solutions. So our solution set consists of 1/3, negative 1/3, the square root of 3 halves, and the negative square root of 3 halves. How do you guys feel about the u substitution?
Eh,
It's a little much, I think. Substituting it into terms of
definitely,
u.
definitely more work.
Yeah. Now there is another way to solve this equation, but I sort of want you guys to get a little bit of time. Let's just take a moment to breathe or finish writing these notes, asking whatever questions you guys need to ask. Because we could have solved this equation not using the u substitution method. You could just simply use the AC method as though you were solving a quadratic equation without substituting it into the u in terms of the variable u. So what I mean by that is that let's look at this equation one more time. And you guys don't have to take notes on this. I just want to show you that if you don't particularly like switching to the variable u and then having to switch back, you don't have to. This thing is in quadratic form, and we could solve this the way we would solve quadratics by just straight up not worrying about that u substitution. We'll just multiply the 18 times 3 the same way we would a quadratic equation. That would still give us the 54. And then we would still go through the process of finding all the factors of 54. So 1 and 54, 2 and what did I say, 27 is what we ended up using. But there's other factors as well. And just for, I guess, in the interest of being thorough, I think 3 works. So 3 and 18 works. I don't think that 4 works. 54 divided by 4 doesn't work. 5 doesn't work. 6 should work. 6 and 9, and I'm pretty sure that's all of the factors. Okay. So if I had been doing my due diligence in the previous iteration of this problem, I would have gone through all the factors. But in any case, we're still going to select 2 and 27 because those multiply to give us our 54. And if we make them both negative, we can get this middle term, the negative 29. Okay. So just like a quadratic, we can split this middle term up and call this negative 2x squared instead, and minus 27x squared. Now, the reason why I'm calling these two terms x squared is because I need to be able to combine to give us the original middle term. And that original middle term was negative 29x squared. So you can think about these two terms that I broke it into as being the children, and they have to have the same name as their parent, right? So they have to have that same x squared, the same variable. And since I haven't done any substitutions here, I'm just going to bring down the 18x to the 4th power and the 3, just like I'm doing the AC method. I can go ahead and factorize this the same way I would doing factoring by grouping. If I look at 18x to the 4th and negative 2x to the 2nd, what they have in common is 9x, sorry, not 9x squared. I got a little bit trigger happy there. 2x squared. Okay. But that would mean that I need a 9x squared here so that those x squares multiply to give me the x to the 4th power. And I would still need a minus 1 here. Okay, so I'm just taking a brief pause to make sure that that does work. 2x squared times 9x squared gives you the 18x to the 4th. 2x squared times negative 1 gives you the negative 2x squared. Okay. On the other side of the equation, they both have a -3 in common, so I'm still going to factor out a -3. And that would still leave me with a 9x squared here and a -1. So when I complete this factorization, I get 9x squared minus 1. Sorry for the handwriting. And 2x squared minus 3. And those are both equal to 0. So what I can do is say that this is 9x squared minus 1 is equal to 0. I will add the 1 over to the other side, so I have 9x squared equals positive 1. And then I'll divide the 9 over to the other side. So I have x squared is equal to 1/9. And then I can just simply take the square root of both sides of this equation. X is equal to plus or minus 1/3, which is the exact set that we got from working it using U substitution. Similarly, when I solve that other equation, 2x squared minus 3 equals 0, I can move the 3 over to the other side, making it positive. So I have 3 is equal to 2x squared. I can divide the 2 over to the other side. So I still get x squared is equal to 3/2. And then finally, I can take the square root of both sides. So I get x is equal to plus or minus the square root of 3/2. And that's what we got from using U substitution. Okay. So the AC method could be used to solve this equation as well. That's typically how I teach my students, but since I noticed that Mary's notes had that U substitution in it, I figured I would go ahead and teach to whatever her specifications are. But there's two ways to go about this. And usually to solve any equation in math, usually there's more than one method. You know, there's more than one way to skin a cat, as they say. I was trying to think of something that was a little bit more humane to cats. But in any case, how do you guys feel about, you know, solving the equation this way? Does it seem a little bit, it's still complicated, right? You're not going to get away from that. Math is challenging, and we're not going to change that. It's been challenging for millennia. But just a strict comparison of that U substitution method versus just using the AC method, how do you guys feel about that?
I feel like I like the AC method a little more. It's a little easier, I think.
Yeah. I mean, I think it's more straightforward, right? Because you don't have to think about what do I call U and then switching back to the world of X instead of having our answers in terms of U.
I'm not the biggest fan of converting it back to terms of X after.
Yeah. I mean, honestly, if I can be real with you guys, when I was taking, you know, lower level math courses back in the day, I remember that I would routinely solve the equations like this, and I would routinely leave it the answer in terms of U, and I would get it wrong because I forgot to switch back to X. So just make sure that you switch back, if you're using that method, switch back to the world of X. Okay. Does anybody have any other questions? It looks like that's the last problem in this set of notes. Okay, I know that was a lot. One more thing that I do want to reiterate to you guys. Let me go ahead and see if I have my Canvas open. Let's see. Let me go ahead and share my screen. Nothing. Okay. All right, so this isn't your Canvas course. This is my Canvas course, but I think that Mary or Miss Cottier has set this up very similarly. My buddy Pete, who is the coordinator of Math World, wanted me to reiterate to you guys that Math World, virtual Math World exists. So if you need to get tutoring for these kinds of equations, you should definitely do that, right? And I always try to reiterate to my students that you shouldn't feel like tutoring is a thing that exists only for you when you are failing, right? If you need even just a little bit of help, you should go ahead and log into Math World and just ask whatever questions you have, even if it's just for clarification. Even if you've solved the problem correctly and you just want to get feedback on, to make sure that you're doing things correctly. So in y'all's Canvas course, I believe that Ms. Cottier has set up a virtual Math World link in the left-hand panel. So I just wanted to remind you guys that these hours exist. So for summer 1 session, which is the session that we're in, Math World is open from 8 a.m. to 7 p.m. Monday through Thursday. Okay. If you scroll down, you can see a list or a table that lists the instructors that we have available. If Miss Cottier explained Math World to you guys again, then this is going to be a boring repetition of that explanation. Math World is the best math tutoring resource that students in the Alamo colleges have available to them, right? And you guys are lucky because it's at St. Philip's. So why is it the best? It's because every tutor that we have in Math World is not simply a peer tutor. They are a degreed professional who has experience teaching the math courses that you guys are seeking help for. So what you will do if you are having trouble or need a little bit of assistance or guidance or just want to chit chat about some of the math problems is that you'll just log into Math World, this Canvas page, through Miss Cottier's Canvas course. And you'll look at what times you have available and if those correspond to the instructors that we have here. So again, my name is Miguel Aguilar. I'm listed here and I'm available in Math World from 12 to 2:30. So if your class usually ends at 1:35 is according to the syllabus. So if you wanted to like leave class with Miss Cottier and you had some questions that you wanted to ask from me, then you are more than welcome to log in Monday through Thursday after your class and just like get a brief rundown or a different explanation, right? But if you don't like the way I teach, and I know that today was a little bit weird because I was covering for Miss Cottier, and I had to go a little bit fast, wasn't sure where you guys were. So I hope that you guys were able to bear with me. But if you don't like the way I talk, if you don't like my explanations, I'm perfectly okay with that. We have other tutors. Just make sure that you guys are getting into Math World and as often as you can before it's too late, right? You don't want to fall behind and then be struggling to work with the tutors in Math World because again, we're not your instructor. We're there as your support. Our intention is not to teach you from the foundation up to where you need to be. I had a student in the previous semester during Maymester that came to me at the end of the semester and said, basically, I need to be taught everything about factorization. And I had to tell them, I can help you and give you some support, but it is not our role here to sort of teach you from the first, square one. But in any case, this support is here. So if you're not sure whether you're falling in the category where you need that help, just log in and ask us some questions. But just know that we are there and we will be here available for you at any point during your summer session. Okay. So that's the last thing that I needed to say to you guys. Does anybody have any final questions for me before I let you guys go?
Well, I have a question.
Okay.
She didn't say nothing about the worksheet quiz that we have to do. It's still open for today?
The worksheet quiz. Okay, so the quizzes and the worksheet quiz, I'm not sure right now at this moment. We're sort of coordinating in the background to figure out what Ms. Cottier wants us to do. So I would say check your emails later or for announcements in Canvas, and we'll try to get that information to you as soon as possible. Worst case scenario, if you don't hear anything by Monday, then we'll just put it off until next week. Okay.
Okay.
Just
okay.
be checking your email for communications from us. Okay.
Okay. Okay. Thank you.
Any other questions? Okay, so if you guys don't have any other questions, you're free to go. If you do feel a little bit timid and do have questions and want to hang back and chat, you can do that as well. But you guys, it's Thursday. You guys have a good weekend and good luck with your studies.
Thank you. Have a good weekend.
You too.